morning, everyone, and welcome to today's webinar on applying GeoAI to video and oriented imagery. My name is Labika Gimler, and I'm the product marketing lead for Esri's spatial data science capability, and I will be your moderator today. Today, I'm joined by my Esri colleagues, who I will let introduce themselves, starting with Omar.
Thanks, Livka. Hi, everyone. My name is Omar. I'm the Director of AI and Machine Learning, and very excited to be with you today.
Hey guys, my name is David. I'm a data scientist on the GeoAI team here at Esri, and I'm working out of Redlands, California. Very happy to be here.
Hello everyone, my name is Angad. I'm a software developer at Esri. Welcome all of you.
And finally, we have Rob.
Hi everyone, I'm Rob Fletcher. I'm a data scientist in the professional services group at Esri.
Perfect. Now, before we get started, I'd like to share a few housekeeping items. First, regarding questions, we highly encourage all of you to post your questions in the questions window that you see to the right of your screen. We will have some time at the end of our webinar to answer some of them. Also, this webinar is being recorded, so everybody that is registered will receive an email with a link to the recording alongside some additional resources, so you can watch out for that. And with that, we can get started, and over to you, Omar.
Thanks, Livka. So with the rise of deep learning, we have been seeing huge advancement in the area of computer vision. And we have started to see this when it comes to geospatial applications, mainly when in the area of extracting data, geospatial data from oriented imagery and videos. So we had previous webinars where we have seen how do we extract features from overhead imagery, for example, and from LiDAR point clouds. Now, today we're going to focus on oriented imagery and videos, and we are going to focus on these two specifically because the amount of data that could be extracted to enhance the geospatial workflows is just amazing, right? So on the top left, you can see our work with different Department of Transportation and local governments on extracting road cracks. So that's an example we're going to shed some light on today. We're not just going to show the example, we're going to dig deeper into what's happening under the hoods, right? So what technology in ArcGIS we're using, how to integrate with custom frameworks, and how to build cool workflows like this. So this is automating the whole process of identifying these potholes and road cracks. On the right, you can see the classic video analytics from CCTVs. So we've been building some capabilities recently in ArcGIS that would help you extract intelligence using deep learning from both offline videos and real-time videos. So we're going to see those two examples today, right? So you can see this path tracing and object tracking on this actually video here, and you can see the other kind of applications of using CCTVs to understand the traffic patterns. Following the same line of detecting road assets, we can see extracting road signs, right? So I've been working with some customers who don't have an updated database of the location of the road signs, the condition of the road signs, the text on the road signs. So as you can see, all of these tasks have been people have been spending a lot of time trying to manually identify these objects and assets. Now with the rise of deep learning, you can automate a lot of this, right? And one of these examples as well is blight and graffiti. So we have been helping some customers detect blight, graffiti, and overgrowth boarded windows on houses at scale, with hundreds of thousands of houses, for example, in 2 hours. So what I want to say is that the applications are endless. Now, how to do this and how to use ArcGIS technology with deep learning technology to achieve this, that's what we're going to focus on today. So this is going to be our outline. It's pretty simple. First, we're going to see how to apply this with oriented imagery. So different kind of applications on dealing with oriented imagery and how to process the imagery and how to extract the location from imagery and a lot of other stuff. Second, we're going to see how to extract intelligence out of offline videos. So you have already recorded a video and maybe you want to integrate it with ArcGIS full motion video, for example. So how you can do this while extracting these objects and features. And third, we're going to see how to do that with real-time video feeds, right? So we have CCTVs, for example, we have those real-time feeds coming, how you can extract intelligence at scale with tens and possibly hundreds of these video cameras and bring this to ArcGIS to do spatial analysis. And we're going to conclude at the end with useful resources, and we would be definitely happy to answer any questions you guys might have. So as Lipika mentioned, if you have any questions, feel free to share it. And we're going to do our best to either reply in real time or save it till the end. So with that said, I want to pass over to David to start with GeoAI with oriented imagery.
Thanks, Omar. So I want to start off by talking about oblique and oriented imagery. And basically, oblique and oriented imagery is imagery that's captured from a non-nadir angle, which is what most of us in GIS are familiar with. And of course, that view of the world, the nadir view, has been obviously tremendously helpful to us for various types of AI-driven geospatial analysis. So think about things like building footprint detection or swimming pool detection. But also in many cases, only looking at the world with nadir means that we're missing out on a lot of information that tends to be pretty high volume, very high resolution, and also these are images that can be geotagged even though it's not necessarily easy to mosaic together. So for instance, data from cell phones, from mobile mapping systems, or from CCTV cameras. So there's also a bunch of workflows that can really only be done from a oblique angle. So things like road asset detection or damage reporting for insurance, or blight and graffiti detection, like Omar has mentioned. So it is important that we explore how AI can be leveraged to enhance workflows that rely on obliques instead of on nadir. And I'm going to present to you some of the projects that we have done in the past that make use of obliques and give you some pointers on how you can begin to experiment with this type of workflow yourself. So I'm going to start off by first talking about road feature detection and geotagging. So this is a very common ask that we're getting from local governments and also departments of transportation, or any kind of institution who have collected large amounts of street level data, who are looking to derive some kind of actionable insight from their collected imagery and also videos. And to do this automatically and at scale, you really have to start to leverage the powers of AI. And so mobile mapping systems, or MMS for short, are essentially these kinds of cameras that are mounted on top of cars that have pretty powerful GPS built into them that's capable of producing high volume and high velocity data like the one you see on the right. And these images are also geotagged as well. So they're geotagged at the time of image capture. So you have the latitude and longitude information associated with every single image. But also at the same time, there's a bunch of metadata that's associated with these images as well. So things like, what is the bearing of the car when this image was taken? What is the row, pitch, and yaw of the camera? And a bunch of other information, such as what is the error associated with each one of these measurements. So these are the types of inputs that we get to play around with for our analysis. And but before I get into some of the project specifics, I want to quickly go over what we mean by road features. And so these are things that are essentially just kinds of assets along the side of the road. Some people also call them road furniture. They are things like road signs, guardrails, curbs, road cracks, pavement markings, what have you. And these are also things that can be visually identified from mobile mapping system imagery. And they are typically used to train a machine learning algorithm. And any kinds of road features really can be detected depending on how much training data you have access to. And the reason behind why departments of transportation or public works may be interested in detecting these road features is to support two business use cases. The first one is being able to manage an up-to-date asset management geodatabase, because various departments of transportation and also public works, they may be interested in understanding where their assets are located, and also they want to be able to update that geodatabase in real time. So that's the first business use case. And obviously the way that this is being done usually is for a lot of these departments of transportations to send workers out to manually survey the entire road network, which, as you can imagine, is typically very, very time consuming. It takes a lot of money to do so. And also it's not very efficient because it takes a long time to completely survey an entire road network. Oftentimes when the road network is fully surveyed, it's also gone out of date. So this is where nowadays, a lot of departments of transportation are starting to use mobile mapping system data. So they're sending cars to take pictures along the road, and then having analysts to manually sit down and then comb through these images, which can be tens of thousands of images, in order to understand where these assets are located. But then again, that is still very, very time consuming, which is why we want to automate this entire process end to end using machine learning. So that's the first business use case. The second one is more in terms of asset status monitoring. So for instance, if departments of transportation are interested in understanding where road signs may be knocked down, or if road cracks started to appear on the road surfaces, they might want to be notified of that in real time. And again, this is something that can be completely automated as long as you have access to street level imagery that's collected once every couple of months or once every couple of years, we can start to run a machine learning model over that output in order to understand where assets may be damaged, or if there's going to be any kind of change in the assets that are being produced, in features that are being detected in the output of the model between different timestamps. So I'm going to talk about a workflow that we've done in conjunction with the Arizona Department of Transportation. So this is something that we've worked on in the past, where we've been able to obtain their imagery and then run a machine learning model over that data in order to understand where road signs are, and also to classify them into MUTCD compliant classifications. So that's about 171 different classes of road signs that we've been able to pick up. And we're also able to pass those outputs into a optical character recognition pipeline. And this is something that's built on top of the Microsoft Computer Vision API in order to understand what text is being written out on those road signs. And then, of course, we're also able to infer what is the latitude and longitude of those road signs in these images, because obviously we have access to the lat-long pairs of the image itself, right? We know where that image is captured, but it's a different matter entirely to really try and infer where those objects of interest are, because then you have to sort of figure out how far those objects are away from the camera, which is not as easy as you would think. And then finally, we're able to output everything into a feature layer, because these outputs are in a format that's native to ArcGIS, that allows you to be able to perform downstream analysis as well. So first of all, how do we actually infer the latitude and longitude of objects of interest? Well, the rule of thumb is if you have access to imagery that's captured at a high frequency, let's say if you have multiple images representing the same object of interest, then the ideal method is to use photogrammetry, because photogrammetry is going to give you just much better accuracy than any other kind of workflows that you can use for this type of stuff. So we would suggest, if you have, let's say, more than 3 or 4 images containing the same object, let's say the same road sign or the same fire hydrant, then simply pass it over to like a photogrammetry workflow, and that's going to help you infer what is the lat-long pair of that object in map space. However, short of that, if you don't really have access to high frequency data, or let's say if you only have maybe 1 or 2 images containing the same object of interest, if you can still use other methods such as similar triangles. So this is useful if you are trying to obtain the distance of an object away from the camera if you know how big that object is in real life. So let's say if you're trying to measure the distance of a fire hydrant away from the camera, because you know how big a fire hydrant is in real life, or you know how large a road sign is in real life, you can use information such as the length of your CCD or CMOS sensor, the size of your sensor, along with, let's say, how big that object is in your actual detected image to obtain how far that object is from your camera. However, what we've done with the Department of Transportation in Arizona is to actually use a different approach, which is to pass the input image into a machine learning model. And specifically, this is a neural network called monodepth that's able to ingest images like you see on the left here, and it's able to output something like what you see on the right, which is a depth map. So every single pixel on that depth map represents how far that pixel is away from the camera, according to the model. So as you can see, the lighter regions kind of represent regions that are closer to the camera, and the darker regions are regions that are farther away from the camera. And this is what that looks like in video. So on the left here, we have the input video. And as you can see, the model is actually going in and drawing out those red bounding boxes around those objects of interest. And in this case, it's road signs. And we have the corresponding depth map being outputted on the right there. And in order to obtain the distance of that road sign away from the camera, all we would have to do is superimpose the depth map onto the detected road signs and kind of find either the centroid of that pixel, or basically average out the value of those pixels and obtain the distance away from the camera. So there's actually a little pitfall here. If you do this kind of workflow, what you would tend to find in the output is that you would have multiple detections in map space, because there's always going to be errors inherent in the way you're measuring in the algorithms that you're using. So typically for, let's say, a single road sign, you might see like a cloud of points that really represent the same road sign, but you have no way of knowing that. So you would see points that are kind of clustered in map space, and then your job becomes a matter of figuring out which points should be clustered together in order to form the same road sign. So there's a couple of ways to do that within ArcGIS. Because this is an inherently spatial problem, obviously we can use something like density-based clustering, HDB scan, or optics. But in this case, we also want to make use of some of the features, some of the attributes that are associated to every single road sign. So we know that the machine learning model is able to output something like the, for instance, the height of the road sign, or something like what is the classification that's been assigned to those road signs. And we know that road signs that are close together in physical space and also have similar heights or similar classifications should inherently be grouped together. So in this case, we instead want to use a tool called multivariate clustering. And there's actually two tools within ArcGIS that supports multivariate clustering. There's multivariate clustering, and there's also spatially constrained multivariate clustering, which is the tool that I'm using for this workflow. And for both tools, actually, the underlying principle is fairly simple. It's making use of the idea of minimum spanning trees under the hood. So the idea is if we think of, let's say, these points as just being points in multidimensional space where each dimension represents the attributes of that feature. So let's say if we have three attributes, right? We have the physical location of those road signs. We also have the height of those road signs, as well as the classification that's been assigned to those road signs by the model. Then we have three-dimensional space, and every single point will be a point in that three-dimensional space. And the idea is if any two points are close together, then it means that they would have to be close together in physical space. They would have to exhibit similar heights, and also they would have to be of a similar classification. So what we can then do is basically, join all these points together where, if points are close together, then we can assign an edge to join those two nodes together. And in order to create the clusters, we would have to basically iterate over the largest or the longest edge that we have and just eliminate that edge in order to create a new cluster. So for instance, if we find that this is the longest edge, we can just eliminate that and create a new cluster. We can keep going until we reach the optimal number of clusters. And the number of clusters that we want to use is something that you can specify as well. So let me show you what that looks like in ArcGIS Pro. So in here, if I zoom out, you'll see that these are the raw kind of detections that's been thrown onto map space, right? And this is just following a route in Arizona. And if I click on one of these points, you'll see that we understand what is the class ID of that point. We understand what is the longitude and latitude that's being inferred using the monodepth network that I talked about earlier, but also what is the vehicle longitude and latitude at the time that this image is taken. So if I zoom in here, you'll start to see immediately that there's points that really should belong together. So for instance, we see that there's this nice little cluster here, which kind of, which intuitively you think should belong to the same sign, and they do. So if I zoom in here, you see that these points really are describing this sign here. And if I zoom out, you see that there's other distinct clusters over here. So the tool that we want to use is spatially constrained multivariate clustering. And all you would have to do is pass in that raw feature layer in this geoprocessing tool. And then you get a choice of what attributes associated with that feature you want to use for further analysis. So let's say we understand that class ID is important. So we want to group all of the similar looking signs, similar signs with the same class ID into unique clusters. We also maybe want to use something like vehicle longitude and latitude, because we know that if the vehicle is taking pictures in locations that are close together, then it probably means that it's the same sign. And we can also specify other hyperparameters, such as what is the maximum number of features. So I speak about features in terms of the GIS meaning of features. So the maximum number of rows of data that can be assigned to every single cluster, right? So let's say we understand how fast that car is going. So we know that we can't have more than 20 features per cluster. So this is something that we can set here as well. And then finally, all we would have to do is specify a spatial constraint. So where that spatial information is coming from. And in this case, we would be choosing something like a spatial weights file. So this is representing a spatial weights matrix. And what that spatial weights matrix is basically just a matrix of all pairs. So it's distance between all pairs. And you would pass that into the tool and you can run it. And in the output, you would get clusters like this. So it is a little bit hard to see, but you can see that there are a lot of points here and every single cluster has its own unique value or color assigned to it. So if I click on one of this point, it's going to show that this has a class ID of 27, and the neighboring point has the same class ID. So we know that this really belongs to the same sign. And then all we would have to do is basically find either the centroid of that cluster or find some kind of average of that cluster and call that the point of interest. And so what that leads to is an operations dashboard that looks very similar to this. So this is, again, a route that's in Arizona. And if I drag this map around, for some reason my Chrome is a little bit slow today. But yeah, you get the idea. So these are the points that have now been kind of aggregated. So every single point really represents a cluster of points. And if I click on one of those points, you'll see that there's additional information that we can retrieve from that point, such as what is the class ID, what is the image that has produced that point, and also if there's any detected text within that point. And a good sanity check is to basically filter these points by the type of road sign. So for instance, if I click on mile marker, here we see that all of these road signs would be filtered by that type. So we see that these are indeed about a mile apart, which is always good to see. And if I click on one of these points, we will see that there's a mile marker and there's a mile marker. Alternatively, we can also filter by signs that have OCR output. So for instance, if I go here and I just click on any arbitrary point, we'll see that this is the sign that's being detected, as well as what is the text that's being recognized in those signs. So going back to the presentation here. So we've talked about automated asset detection, and really asset status or damage monitoring is the same workflow as what I've just talked about. But let's say there's a need for new asset installations, or if work crews find out that there's certain road signs that's been knocked down and need to be moved around, is there a way for them to basically update that geodatabase in real time? Well, it turns out there is, and there's actually a suite of ArcGIS mobile applications that we can use for this type of workflow. And in fact, for this exercise, we've been using ArcGIS Collector in order to validate all of these points that have been detected with our machine learning model. So we've sent someone to drive along this route using ArcGIS Collector to validate all of those points, and also maybe make some slight adjustments in case there's some errors in either the classification of those road signs or in the geolocations of those road signs, and have everything output on a dashboard here. And basically that geodatabase would be updated in real time. So a common question that we get quite a lot is, how can I get started with this today? And this is, questions that would be asked by people who don't necessarily have access to a lot of data. So they may be thinking about having some kind of proof of concept, in which case you would have very sparse data. You probably don't have a lot of labels. Is there a way to make use of that sparse data and still create a fairly good machine learning model? Well, the answer is yes. And in that case, we would use something like image augmentation. And what image augmentation does is it takes your input data, so your image and also your labels, and it performs a series of random affine transformations on top of that image. So it would do things like random cropping or random rotations, distortions. It would stretch the image. It would also do random dropouts. So it would selectively block out certain regions in that image and just completely erase that data into like 0. And it would also do random chromatic shifts. And the point behind it is that you would basically increase the amount of training data that you have by like 5-fold or 6-fold. And in the output, you would basically have a model that's not overfitting on just the sparse data that you originally had. And if you're interested in finding out more about image augmentation, it's actually a function that's available within the ArcGIS API for Python. It's called prepared data. And what that does is basically taking your image and it applies a series of random affine transformations on top of that. And it would give you images that look like this, where it's distorted and rotated and so on. Also, if you're interested in basically training your own machine learning model on top of a publicly available data set, we have a MUTCD compliant data set that's kind of published by the University of Vermont. And it's MUTCD compliant, meaning that it's a set of common traffic control devices that's published by the Federal Highway Administration. And there's actually a link that I have here. And basically, it's a project that's supported by the Vermont Artificial Intelligence Lab. And if you go to data sets here, there's a series of images and also labels that are publicly available. And it's actually divided into two data sets. There's challenging and easy. And easy is basically around 78 labels. You have around 8,000 training images. And challenging is the full 171 classes of labels, as well as about 18,000 images for training. And we've gone in and trained a machine learning model over the challenging data set in order to get this type of output that you see here. So on the right, we have the ground truth, and on the left image, we have the detected output. And as you can see, even though these signs are pretty far away from the camera, the machine learning model is able to detect them and classify them. And it doesn't really matter how many road signs there are per image, the machine learning model is able to go in and detect those signs nonetheless. So that's for road signs. I want to quickly switch gears and talk about road cracks and water meters. And basically, as you can imagine, this type of workflow being applicable to any kind of road feature that you can visually detect. But just to give you an example for road cracks, this is something that, again, departments of transportations may be interested in, because there's multiple types of road cracks that convey different information about the quality of the road. So there's things like alligator cracks, there's transverse or longitudinal cracks, and it's important to be able to not only detect those road cracks, but also classify them into the correct type and have everything display in an operations dashboard. So this is what you see here. So we're able to run a machine learning model that's ingesting data that's captured from a dashcam video feed, and to produce bounding boxes like what you see here and throw everything onto map space. So then you have an idea of what is the severity of road cracks along different segments of roads, so you can start to prioritize where you want to begin fixing the roads. A slightly different workflow is water meter detection. So as you can see here, we're no longer operating with bounding boxes. Instead, we're using semantic masks. And what semantic masks are basically class values that's been assigned to every single pixel. So what we see here is an input image, and the model has been able to look at that input image and assign values of 1 to regions where it thinks there may be a water meter. And in fact, if we superimpose those two images together, we see that the model produces some fairly convincing outputs. And actually, these are all images in the test data set, so these are images that the model hasn't seen before. So to quickly recap, this is what that architecture would look like, and it's the same for road cracks, for road features, and also for water meters. We would first start off with some kind of raw mobile mapping system imagery in a folder, and you would also have your metadata stored in that same folder, either as a CSV file or as EXIF data stored in those imagery or in those videos. And then you would simply pass that into your machine learning model. And typically this would be a model that's running on an ArcGIS notebook or a Jupyter notebook. And for the case of road sign detection, we're also using the Microsoft Computer Vision API in order to use their optical character recognition pipeline. And finally, all of these outputs are stored in a tabular data. And the reason we're storing this in a tabular data is so that we can push this to ArcGIS Pro for further analysis using clustering. And of course, this is not necessarily something that you have to do. You can also do the clustering analysis completely within notebooks as well using ArcPy. And then finally, we're pushing everything into a hosted feature layer that's being displayed in ArcGIS Online and then pushed over to an operations dashboard where we can see data being populated in real time. And in order to support asset maintenance or new asset installations, we're also bringing in ArcGIS Collector. Of course, you can swap this out for something like ArcGIS Workforce, Survey 123, or Quick Capture. That's up to you. But all of that would basically be able to update that same geodatabase and for those changes to pipe in through operations dashboard. So what if you're interested in standing up that optical character recognition service today? How would you do it? Well, it's actually fairly simple. So all you would have to do is have access to an account. And in fact, this is a free service. So there's two tiers. There's a free tier and there's a paid tier where you basically have access to more hits on that API server per minute, and also you have a faster response. And in order to access that service, all you would have to do is search for cognitive services within Azure, and you can add a new service, and it would be called Computer Vision. It would be under the AI and machine learning tab here. And here it is. You can choose to add that service. Now I've already created a service, so I'm not going to add that. But basically, once you add that service, you can go inside, and there's actually a fairly useful quick start guide that you can use to basically start running that service straight away. And if we go into that quick start guide, it gives you code samples as well. So all you would have to do is copy and paste this entire code sample into your ArcGIS notebook or Jupyter notebook and run it. And it's going to be able to produce an output that's very similar to this. So this is a notebook that's performing inferencing on top of input imagery. So that's the images from the Arizona Department of Transportation. And what we see here is, first of all, the model is producing bounding boxes on top of detected road signs. And then what I'm doing is basically taking those bounding boxes, creating a buffer around it, and then using hue lines, I'm able to orient this road sign so that it's basically horizontal. And then I'm passing it off to that service, that computer vision service that I just talked about. And what you would get in the output is something that looks like this. So it's a little bit faint, but you can see it. It's text that's being superimposed on top of that image, where this is just completely detected by that computer vision API, and it's outputting exit 27 here. So what if we want to really accurately locate road features? So there's actually another way to do this, and that's to use a semantic segmentation workflow as opposed to a bounding box workflow. So we know that the state of the art on semantic segmentation has been very, very good recently. So this is the type of output that you can expect to see using state-of-the-art models. And in fact, there is a couple of models that's already available within the ArcGIS API for Python. So there's UNet, there's DeepLab version 3, there's MaskRCNN, which is more instant segmentation, but it's still largely similar. And the idea is we can basically very easily create a geoprocessing tool that takes in your original input image, and it would first pass the image into your segmentation model of choice, let's say UNet, and it's going to be able to produce those segmentation maps, seg maps. And also it's going to use something like monodepth in order to create a depth map as well. And using those two inputs, it's going to be able to create a point feature class for you that represents your object of interest. So this is what that would look like within ArcGIS Pro. So again, this is just a very quick geoprocessing tool that we put together that is taking in your original input image. You can also specify what type of object that you want to detect and throw onto a map. And in your output, you're just going to get a point feature class that represents your detected objects. And there's actually also a notebook that I can show that talks about this. So this is a notebook that does pretty much the same thing, where we are using, first of all, the monodepth model in order to understand what is the depth map of your input image. We're then able to basically run a segmentation model over your input image and combine that with the depth map in order to understand how far objects are away from the camera. And so what we see here, it's a little bit small, I can make this a little bit bigger, is these are centroid points on these kinds of contiguous blocks of pixels that represents the location of that object, right? And you can use that to infer the distance away from the camera. So to wrap up, there's actually some new changes that's going to be made to Pro 2.7. And primarily, these are changes related to basically being able to enhance your deep learning workflow within image space. So typically, when we talk about these kinds of deep machine learning geoprocessing tools within ArcGIS Pro, it's always within nadir space, right? It's within properly georeferenced images from a nadir angle. But let's say we have access to drone footage of specific locations where it's very oblique. So for instance, what you see here is the oblique input into those kinds of geoprocessing tools. And as you can see, it's very, very difficult to manually sort of pick out objects of interest because of how distorted it is. And the new changes that are coming in 2.7 and basically allows you, allows the model to convert that oblique angle into more of a just an adjusted angle where the images are not as distorted. And all of this is completely transparent to your workflow, meaning that you can pass in oblique imagery, and it's going to be the same workflow as if you're passing in nadir imagery. And it's going to do that conversion under the hood, and it's going to run that deep learning model and convert it back into your oblique angle. And also, for images that are not necessarily projected onto a map or cannot be projected onto a map, the user can also complete the deep learning workflow within image space as well. So that's all coming in Pro 2.7. So quick summary, we've talked about how we can use deep learning for feature extraction from oriented and oblique imagery. We've talked about how we can accurately geolocate assets using either bounding box labels or semantic segmentation maps. And we actually talked about several ways which we can use to ascertain what is the location of those objects of interest. And then we've also talked about how do we use computer vision API from Microsoft in order to use their optical character recognition pipeline. So now we're going to very quickly switch gears and talk about offline video analytics within ArcGIS using full motion video. And for that, I'm going to pass it on to Angard.
Thank you, David. So today I will be talking about how we can use ArcGIS Learn to find interesting artifacts within a video. To do that, I will be taking the case of an invasive species of the catfish, the blue catfish. The blue catfish is an invasive or a non-native species. By this, what we mean is that over a period of time, the species has moved from their natural habitat to a new environment. And in this new environment, they have an advantage over other species. This can often lead to economic or environmental damage. We often refer to this term as biopollution. The native distribution of the catfish is in the Mississippi region, which is highlighted in red over here. Although over a period of time, this species has been moving towards Virginia, and now they occupy the region in white over here. Now, since this species has been moving throughout Virginia, they have occupied almost every major river system in the Chesapeake Bay region. And it's necessary that we study them. Why? Because they're in the new environment, they are on the top of the food chain. They are the topmost predator, and they have been consuming some other species, commercial species like the American shad and the blue crab. It's necessary that we perform some analysis about the species. It's necessary that we perform some growth calculations. We estimate their population structure and their general abundance, and we provide this information to the necessary stakeholders. To do this, we often use drones and we capture videos of this species. We often use a method called low voltage frequency electrofishing to encourage the fish to come towards the surface of the river. And this is a non-invasive method. This is a sample video which has been captured using drones, which shows the abundance of the catfish in the Chesapeake Bay region. Now, since I mentioned that we need to perform these calculations, if we were going to do this calculation manually in this video, and if you were to mark each catfish in this video manually and track them throughout the video, it's going to be incredibly painstaking. So this is where deep learning is going to come into picture. In ArcGIS Learn, we have plenty of models available for different use cases. We have object detection models, we have feature classification models, we have pixel classification models, instance segmentation, semantic segmentation, and recently we added point CNN and tabular learner models to the list. In this case, we are going to train an object detection model to find catfishes in the video. We will be taking single shot detector for our use case. The first line imports the single shot detector class and the prepare data function which performs data augmentation as David mentioned earlier. We pass in the folder structure containing the images and the labels, and the prepare data function returns the augmented data to us. We use this augmented data and initialize our single shot detector object. Using the LR-find function, we are able to find a good learning rate, and using that learning rate, we fit our model for 300 epochs. We see that the average precision score comes around 83.5%. Using the show results function, we can visualize the prediction ground truth versus the predictions. We can see that in almost all the cases, the model is able to find out all the images and it's performing really well. Coming to the predict video part, since we see that in show results, it's able to perform really well, we can now predict on a video. The predict video function is very simple to use. We just pass in the input video on which we have to perform the predictions on. The second parameter is a metadata file. The output of the predict video function is going to be appended to this metadata file in the form of a VMTI. VMTI is a full motion video multiplexing compatible format. We'll come to this part a little later. The primary output from this predict video function is in the form of VMTI. However, sometimes we want to visualize the results. To visualize those results, we can easily pass a parameter called visualize equal to true to this predict video function, and it saves another video output file in the same folder as our input video file. As I mentioned before, that in our catfish sample, we have to track each catfish throughout the video. To do that, we can pass a parameter track equal to true. This initializes an algorithm called SORT, Simple Online Real-Time Tracking, and using this algorithm, it tracks every object detected within the video. So we can easily track every catfish in the video and make the necessary calculations. Now, as I mentioned before, the prediction results from the predict video function are saved in a VMTI format. This VMTI format is full motion video multiplexing compatible, but to perform full motion video multiplexing, we also need some necessary data related to the video. For example, in our case, we have information like the sensor latitude, sensor longitude, frame center elevation, frames. Using this information, we can multiplex the video and visualize this output in ArcGIS Pro. I've already run the predict video function, and this is the output which is generated from the function. We can track the catfishes detected through the video in ArcGIS Pro. Sometimes we also need to customize our predictions so that we can properly display and properly visualize the results. To do that, predict video function provides us plenty of options to customize the predictions. For example, to customize our visual options, we have options like show scores, show labels. We can disable them or we can enable them based on how we want the outputs to be. Similarly, for the tracker, we have options like vanish frames and detect frames. Vanish frames tells the tracker that if an object is not detected for 40 frames in this case, then we have to stop tracking it. Similarly, if an object is detected for continuous 10 frames, then we have to start tracking it. This is another sample output that has been generated using the predict video function. In this case, we have disabled the show scores and show labels option, and we can see that the model is performing really well. Now I would like to hand over to Rob.
Thank you, Angad. I'm going to talk quickly about doing GeoAI with real-time videos. Angad showed when you can record videos from things like drones and stuff like that. And I'm going to go onto the case where we might have CCTV cameras or cameras over intersections, things like that. So real-time video analytics allows you to make much better decisions in a multitude of instances because you're getting the actual real-time information that you need. It can produce data that before was kind of impossible to get a hold of just because of the volume of labeling or human power that you would need to do this. And then we can couple this with AI. This real-time data can be generated in finer grain than ever before. One way I think about this is that you kind of go from occasionally counting things to now in real time being able to count things like people, cars, trucks, bicycles, etc. All of this all at the same time. So here's a quick example of, this is actually a real-time video of, it was a recorded video of us doing processing on 12 real-time video streams all at once. And this was done just with my local desktop, which can actually do quite a few more video streams than this as well. But so this is just an example of being able to actually do this kind of detection on several video streams all at once and multiplexing them together. So the way that we're doing this is we're working with NVIDIA. NVIDIA has developed a framework called Metropolis, and we've been working very closely with them to integrate ArcGIS capabilities with some of their deep learning capabilities. So this is a quick example of the Metropolis architecture. I'm not going to go in detail through this, but it has a couple of major parts, which is the sensor processing you see over on the left. This is the kind of section of the pipeline that is responsible for doing the deep learning, producing these bounding boxes, things like that. And then that moves over to a Kafka broker, where in Kafka, this is the way that you store messages. So you can store all these bounding boxes so that they can be consumed by various different components. And then you can move on to some streaming analytics, where there's all sorts of things that you can do based on what is the result of these bounding boxes. And then data storage, API, and visualization UI all come from these things as well. To talk a little bit more about the actual integration with the Esri platform, here's just sort of a simplified view of Metropolis here. We can see that it takes, collects this imagery and can decode it. So this means that, you can take imagery from lots of different sources and lots of different formats, and there's hardware accelerated decoding that can happen. There's also some pre-processing and some deep learning that can happen. This all happens on the GPU, so it's very, very fast. This includes things like generating those bounding boxes, classifying the bounding boxes. So for instance, finding out, is it a car? Is it a person? Maybe what kind of car is it? What color is the car? Things like that. This also includes some interesting things like de-warping 360-degree videos as well. So you can take something that's any one of these types of 360-degree videos and actually de-warp it to make it a square video so that it can be run through these deep learning models that were maybe only trained on square videos. And then we can do some tracking on the back end of that. So this is, just like Angad talked about, associating a single ID with an object moving through frames of video. And then we can do things like re-encoding the videos, compositing them, all sorts of things like that, and then push them out to this Kafka message broker that can then be consumed by the ArcGIS platform. Things like GeoEvent or even the new analytics for IoT can pull directly from these. And then the entire sort of suite of analytics that you can perform using the ArcGIS platform are available to you on this very, very rich data, and that can be then also visualized in things like Pro or dashboards, any kind of real-time monitoring in there. So I'm going to give you a couple of examples here as well. This is an example of running this real-time detection on, I think this is 40-something cameras in Dubuque. So you can see this is a real-time dashboard of each one of these cameras actually detecting cars and pushing all of that information into the ArcGIS platform to be displayed on here. So you can see the where each of the cameras are pointing and also the counts of cars at each one of them. So this allows traffic operations departments to do all sorts of very interesting analytics by looking at real-time traffic flows based on time of day, maybe even correlating to sporting events or weekend activities, things like that. And so they can really understand how the streets are being utilized inside of their city. Here's another example of that. This is just for a single camera, but you can just kind of see what's happening in this video, how it's counting these cars in real time, and it's trying to estimate what sort of portion of them are cars versus trucks versus buses, things like that. And is another example. This is one using similar techniques in Washington, D.C. This is actually running, I think, 140 cameras. So this is 140 cameras all being displayed in real time, getting the information about what's happening throughout the entire city. And then taking this information, we can also do things like anomaly detection. So this would be, instead of just counting and understanding volumes, we can look at how that differs from historical averages. And so we could see if there are pedestrians above what we would normally expect at a given time. This can inform, again, traffic operations or law enforcement. So if there's a lot of pedestrians moving through an area and we don't normally see that many pedestrians there, maybe we could dispatch a police officer to direct traffic just to make sure that people crossing the streets are all safe. So shifting gears just a tiny bit, instead of CCTV cameras, this is an example that we created based on drone video. So like Angad showed as well, using drone video, this is something else where we are consuming drone video, running custom models on it, and we are also performing some georeferencing kind of in real time as the video is going, where this green box that you see around the parking lot there is actually georeferenced to the video and will move with the video as well. So it's all gets stuck in the right spot. And so for this, you can do analytics with things like, detect whether cars are speeding or not. You can look at their trajectory to try to understand, okay, how are cars using these parking lots. So this is something that, for say like retail could use in order to understand how how customers actually use their properties. Where do they park? Where do they not park? What are the sort of typical traffic patterns? And things like that. And so this type of a workflow can be done by first, building and running your vehicle detection model, and to get the location of all of these cars in the video. And coming along with this is a custom model we built that actually does the georeferencing kind of on the fly as this video is running, so it can produce the lat-long coordinates of these as the video is going. And then this allows you to export the data in a vector data set, so tabular, a couple of other ways of doing this as well. And from there, once you have all this tabular data, there's just a wealth of information that you can get from it, and any analytics that you would want to run on it are all possible. I'm going to pass it back over to Omar now to wrap up.
So this concept could be applied to a lot of use cases. This is an airport, for example. You can track the movement of the crowds in an aggregated fashion and understand the flow of people inside facilities. And you can take this concept and, for example, apply to things related to COVID, like social distancing. This is some experiment that NVIDIA is doing in this capacity. So if you're interested in trying this out, just let us know. We would love to work with you on trying this out, where they are trying to infer the distance between people, right? And send alerts, possibly if social distancing is violated. And if you think about it, you can extend that concept to something like this, right? So in a facility like an airport or a workplace or anything really, you can use this bundled with ArcGIS Indoors for indoor mapping and possibly GeoEvent for real-time alerting capabilities like that one here. So you can quickly understand where violations for social distancing are happening and where you need to take measures for that, right? A couple of other use cases include some work that we've done with Cobb County before, trying to understand or estimate the amount of crowd coming up from a sports stadium so that we can optimize the traffic lights. As you can see here, instead of manually doing this work, you can bring some automation to optimize street lights so that they can open or close based on the flow of people. This is a detailed set of use cases that we're going to share with you when we share the presentation. So as you can see, the use case that Rob went through, video analytics with real-time feeds, when it comes to transportation and local government, for example, it could be applied in two main directions. A strategic kind of planning direction where you can understand more about the traffic patterns, like understanding the infrastructure utilization, like how many trucks or bicycles are passed through streets, where do we want to invest in more resources and stuff like that. Or it could be used in more real-time kind of operational scenarios, like proactively dealing with congestion. You can quickly understand where are some spikes in congestion to deal with it in real time. You don't need to wait for 10 minutes or 15 minutes for someone to report that, right? Same thing with car crashes. You can train models to detect car crashes, right? So anything that you would like to understand in real time and spot out of hundreds of CCTVs or maybe thousands, you can bring automation to this, right? So being it congestion, road crashes, you name it. And obviously you can then leverage the spatial analytics in ArcGIS to build information of that. And that's why we're excited to bring this capability to ArcGIS, because it's not just about detecting things, it's about the spatial analytics that could be done both in real time and on a strategic level. That's the kind of the overall flow of this solution. So it ingests videos from RSTP feeds, and then it passes this through Metropolis for the inference, and then pass it to GeoEvent for both visualization and storage in the big spatial temporal data store. Storage is really useful here because you can get back in time and understand patterns per time of the day, day of the week, and you can do different kind of analytics like anomaly detection, for example. And this is just the beginning, right? Once you have this in the GIS, you can do a lot of spatial analytics like event planning if you want to optimize resource allocation in real time, for example, or situational awareness if you want to receive real-time alerts and understand what's in proximity. So think about the possibilities when you add the spatial analytics on top of the detection capability brought by deep learning. I want to share with you a couple of useful resources, and we're going to share these with you in the presentation. So we have a notebook, a publicly available notebook that is showing how we are using ArcGIS to learn, predict video, to deal with video feeds, to detect road cracks, and this is the link for it. We have a detailed blog post on our Medium blog. I really encourage you to go to medium.com/GeoAI, and we have a lot of blog posts detailing our work, one of which is road feature detection and geotagging, which is pretty much what David showed today. Part of it, at least, explaining in details how to do that work and do the extraction of geolocation and stuff like that. We have two links here for ArcGIS Notebooks and Notebooks Gallery. So ArcGIS Notebooks is a powerful tool that can help you integrate both publicly available data science libraries in Python along with ArcGIS, right? It's available with Pro 2.5. It's available with ArcGIS Enterprise 10.7 Plus and recently available in ArcGIS Online. So start having a look at ArcGIS Notebooks. It can help you do a lot of these workflows. And there is a beautiful notebooks gallery here. The ArcGIS API for Python is essential for this kind of work as well. It enables you to integrate with publicly available frameworks easily back and forth between ArcGIS and different kind of data science, machine learning, deep learning frameworks, and the GeoAI blog as well, as we mentioned. Angard showed today an example of integrating feature extraction from videos with ArcGIS full motion video. So this is a capability that you can know more about from this link as well. Finally, I'd like to invite you to join the LinkedIn group for GeoAI. It's a public group that we have on LinkedIn where it's meant to be a community to share different ideas and resources and have conversations about GeoAI, which is the intersection of AI and location intelligence. So please join the group and feel free to invite others. We have a lot of good discussions there, and we frequently share resources and events.
We can move on to questions. So to get us started, the first question for anybody on the panel is, how much of your day-to-day is pulling from general data science knowledge versus how much of it is specific to Esri products and solutions?
I can take that one. So obviously there is a lot happening in the data science and the AI space, right? So we don't want to reinvent the wheel. Our strategy is to try to make as much as possible usage of available frameworks. That's why we invest heavily in integration, right? So we have the ArcGIS API for Python that enables this kind of integration. For example, we're invested in ArcGIS notebooks that can help you bring in those machine learning, data science, deep learning libraries, right? It comes pre-configured with almost 300 plus data science libraries and machine learning. On the other hand, we try to invest in two things. First, invest in machine learning algorithms that can work seamlessly with geospatial data. So for example, forest-based classification and regression is a tool in ArcGIS that you can use to make predictions, and it can easily consume geospatial data, whether these are feature layers or input rasters. So we try to make it easier to use the existing machine learning algorithms. That's one thing. The other thing is creating spatial machine learning tools. So there are some models that are inherently geospatial, right? Like geographically weighted regression, which has different types like logistic regression and can predict quantities and stuff like that, and spatially constrained multivariate clustering. So these are like spatial machine learning algorithms. So I think my answer is we try to integrate with external frameworks. We try to build capabilities that can help bring in data science libraries, and we try to build spatial machine learning tools.
Absolutely, thank you. And I know we're at time, but we'll probably just fit in one more question. And for anybody whose questions weren't answered, we will be following up with you, making sure that you have some responses. But the last question that we can cover today is, when running GeoAI on oriented imagery, is it better to use a single direction camera like a GoPro, or can you use panoramic photos from a 360 camera? And are there specific cameras that work better for these kinds of applications and workflows?
So
I can take this one.
Yep, go ahead.
It really depends upon the type of workflow that you're wanting to do. 360 degree cameras can absolutely be used. A lot of times they need to be dewarped because often the model that you will be running on it was trained on something that wasn't a 360 degree image, and so that will warp the bounding boxes around a little bit. However, if you train on that video, there's no need to dewarp it. Sometimes it is a lot better to use a directed camera though, as the only information that you're looking for is directly in front, or you need it from a specific angle. And so it really kind of depends upon the problem that you're solving, but either can be used. And as far as the quality of the camera, it kind of depends upon the job that you're trying to do. Obviously, if you have a very high flying drone and you're trying to detect very small objects, you're going to need to have a very, very good camera in order to actually be able to see those. But for some things, they don't need to be as bad. For instance, the road signs, you could imagine being able to do that just with a GoPro on the dash, as long as you have good GPS location. And this is because GoPros do take fairly good video. Really, you just need to be able to see the object in the frame in order to be able to do it. And so with some of the lower cost cameras, you can actually get very good results as well.
Awesome. Yeah, and I think with that, we should probably start to wrap up. Like I mentioned, we will be sending out an email at the at the end of our webinar with access to the resources that were shared alongside with the recording. Again, we want to thank the panelists for their time today and for your questions and engagement, and hope to see you at our next webinar and that you have a great rest of your week.